Hi and welcome to this section where we are going to continue our study of matrix algebra by looking at matrix multiplication. So the purpose of this section is to develop the concept of matrix multiplication as was introduced in the previous section. So in the previous section of our resource book, which is 3.4, you read through. They are simply trying to give a historical perspective how the famous mathematician Arthur Cairo came up also these important patterns that helped us or shaped in defining what matrix multiplication is. So they are just giving a historical perspective and so on. However, in here, of course it is important for us to know that, but we shall get to the point straight away here by saying that it is helpful to begin by considering a single row here, okay, made up of these entries R1 up to Rn, and a column vector here consisting of these entries C1 up to Cn. So we define the standard inner product of R and C to be the scalar, which is defined as getting the entry here R1 times the first entry in the column and the row times the first entry in the column, the second entry in the row and the second entry in the column, and so on up to the last here and the last entry in this row and the last entry in this column. So you realize that the entries here in this row should be the number, the size should be equal to the same entries in the column here. So that is why we are saying R1, RC1 plus R2, C2 plus and so on, and which you can write in short form as the summation from I is equal to 1 up to n, Ri, Ci. Okay. For example, if we have this row here which has these three entries and this column which has these three entries, the standard inner product is simply going to be 2 and times 1 plus 4 times 2 plus negative 2 times 3. Okay. So previously also, you will see that the product of a 2 by 2 matrix F with entries A, B, C, D and G with entries A, B, C, D, okay, was naturally defined as follows, okay, that is H, okay. Now they are just copying it from up there. However, I would like to define this by use of what we have just seen here, the standard inner product. So this was what was seen, okay, previously. However, defining it by using our standard inner product, we realize that this is H, okay. So this small H11 is simply representing this entry here in the first H11 in the first row, first column. This one here, first row, first column. Similarly, H22 is this one here in the second row, second column. H12 in the first row, second column. Which one is that? First row and in the second column. Okay, it is in the first row and in the second column. Okay, so we realize that H11 is simply the product of getting the first row of F multiplied by the first column of G. Okay, so this is what it is just saying here. You get the first row of F multiplied, you get this inner product, standard inner product of the first row of F and the first column of G. To get the entry in H21, we are going to get the standard inner product of the second, look at this here, this one here, of the second row of F times the first column of G. So let us see here. So you see CD is the second column of F, okay, and AC is the first column of G. So it is just this row and this column here. So we can see that if it is, we want to get the entry here in the second row, second column of our product here, H, the product H of F and G, we are simply going to get the inner product, standard inner product of the second row of F and the second column of G, so that we shall have CB plus DD, CB plus DD. In other words, whatever, okay, maybe I haven't mentioned, the star here simply means, if we write F1 star, it simply means we are getting the first row, because the entry 1, remember the F, the matrix, we are representing it as Fij, I representing the row and J representing the column. So in the position of the row we have 1, but in the position of the column we have star. The star means all columns. So if you write F1 star, we simply mean this whole row, okay, this row, first row, and all the columns. If we write H1 star, it means the first row of H throughout all the columns, okay. If we write H2 star, we are meaning the second column, the second row of H, okay. If we write H star 1, that means that we are saying that H star 1, the 1 is in the position of the 1 is representing the column number. So if it is H star 1, we are meaning we are looking at all rows of the first column of H, that is H star 1, okay. So this is just the notation. So in summary, this whole part here is simply telling us that we can deduce a matrix multiplication to be just standard inner product of row by column. So I'm sure you may be familiar with that if we are multiplying two matrices, it is just row by column multiplication. That is what we call the standard inner product, row by column, row by column, row by column, okay. Now so we would like to define here what matrix multiplication, some more details on matrix multiplication. So you say that if we have matrices A and B, they are said to be conformable for multiplication in the order AB, A times B, whenever A has as many columns as, whenever A has exactly many columns as B has rows, i.e. the number of columns of the first matrix should be equal to the number of rows of the second matrix. So A has M columns and M rows and P columns, okay, while the matrix B has P rows and N columns. So we see that the number of columns of the first matrix are equal to the number of rows of the second matrix. Therefore these two matrices are conformable. Conformable meaning that yes, they are compatible for multiplication. If this is not so, then it is not going to be possible, okay, because remember we are taking the standard inner products, okay. And the result here will simply be, because this is what we check that this is equal to this, so it is conformable, and then the result of AB is going to be of order M by N, okay. So yes, so that is what we have here. And what else do they say? Yes, I think that is all they are describing here. And then in here they are saying that the matrix, so here they are telling us this notation here, A, B, I, J. They are simply telling us that when we multiply A times B, the entry in the I, J position of the product AB is simply going to be that, okay, which is got by taking A I star, okay, this product, remember we say that we are taking row, okay, by column multiplication, so that we are getting the ith row of our matrix A, and then we are multiplying it by the jth column of our matrix B. Okay, so this is just exactly what we have just said. So we just pick the I. Okay, in other words, if I is 1 and J is 1, that means AB 1 1, the entry in the first row and in the first column of the product AB is the result of getting the first row of A, taking the standard inner product of the first row of A with the first column of J. So whatever is just being written here is just exactly what we have seen, the standard inner product. Okay, so okay, so for example, this can make quite, it can make our life quite easier. For example, if A and B is that, I don't know, then the product AB exists. Why? Because A has 2 rows and 1 2 3 columns, so it's here 2 by 3, and then B is 3 by 4. So they are saying that this one here, the inside ones match, i.e. the number of rows, the number of columns of the first matrix equals to the number of rows of the second matrix, so they can match. The inside ones match, that means they are compatible. And then the outside ones here will tell us the shape of the product, i.e. the result is going to be a 2 by 4 matrix. Okay, and then what they are simply telling us here is what we have explained there, or what I was trying to explain here, that if you want to get the product, the entry of the product which is in the second row and in the third column, this one here in the 2 3 second row third column, which one is that? Okay, the product is not written here. Okay, the second row and the third column of the product AB, we are simply going to get this one here, the second row of A, and then everything. Okay, the second row of A, all the columns, that is why the star is there. Then we are going to take its inner product with the third column of B, this one here, which is in a box here, in a rectangle here. So this is what they have just been trying to explain here, in case I did a terrible job at explaining it. That is exactly what is being done here. Okay, so you may not, that is just for us to understand, but take home is it's the row by column. For instance, if this is A and B, you check if they are conformable for multiplication. So the entry here is simply going to be the result of 2 multiplied by 1 plus 1 multiplied by 2 here plus -4 multiplied by -1, i.e. the first row here and the first column here. So we know 2 times 1, that is 2, plus 2, that is 4, and then the -4 times -1 is +4, and then 4 plus 4 is 8. So that is it, and so on. Okay, I'm sure you can go through that, just follow the same ideas, and then yes. So in spite of the fact that the product AB exists, so you will try to find out that that actually BA does not exist because they are not conformable, i.e. B is a 3 by 4 and A is a 2 by 3. So you realize that these columns here are not the same as these ones here. The inner ones do not match. Okay, i.e. the inside dimensions do not match. So even when the products AB and BA exists and have the same shape, they need not be equal. So these are just various scenarios of telling us that maybe we have AB is 0 0, and then BA, it also exists, but then they are not the same. Okay, so we know for a fact, and it is written here in quite bold, that matrix multiplication is not commutative. EAB is not equal to BA. Okay. And then also for scalars, something else to note here for matrix multiplication is that for scalars, we know that if the product of two scalars is 0, that implies that either one of them is 0, i.e. either alpha is 0 or beta is 0. However, for matrices, this does not hold. Okay, if the product of two matrices AB is 0 and A is not, with A not 0, it is possible, for the product of two matrices to be 0 with A not 0 and B not 0. Okay, I think because we have already seen here AB is the 0 matrix, yet A is not the 0 matrix, and neither is B the 0 matrix here from this example 3.51. okay, we have already seen that. So those are quite some interesting things. And then related to this issue is somewhat what we know as the cancellation law for scalars. Okay, it says that if we have scalars that alpha times beta is equals to alpha gamma, then we know that we can just cancel this alpha, and then we have that beta is equals to gamma here. Okay, yes, but for matrices it does not actually hold. Okay, the cancellation law for this matrix multiplication fails. For example, A and B is here, and then you have C. So you will work out and find out that AB is this 4444, and also AC is also the same 444. But so ideally we would have to say that, okay, let us, if AB equals to AC, then we can cancel A and B equals to C. But in this case, we actually see that B is not equal to what? To C, and in spite of the fact that A is also not equals to 0. So, and then what else here? They talk about various ways. So this is just terminology. You can really read through it and attempt the rest of the exercises. Yes, so we'll see you in the next video. In case there is anything you don't understand, please feel free, put in the comment section and we will refer to it. Thank you, and see you in the next video.